Section 10.5 gas mixtures. So we're going to talk now about what's called Dalton's Law of partial pressures. This is the same Dalton, John Dalton, who developed the modern atomic theory of matter. Okay? So the idea here is essentially one very simple postulate, and that is that if you have a mixture of gases, so for example, let's say we have some kind of container that has gases in it, and let's say that it has oxygen, helium, and hydrogen. Okay, there's 3 gases in there. What this says is that the total pressure of this mixture, P total, is equal to the sum of the individual pressures. Partial pressures, we call them, because it's part of the whole. Okay, now your textbook puts this as sum of the individual pressures. Okay, so if we have 5 gases, the pressure of each gas added together would be equal to the total pressure. Very simple relationship. So let's say, for example, that we have 2 gases. Let's say that we have oxygen and nitrogen. They're both gases. And the pressure of the oxygen is 4.48 atmospheres. And the pressure of the nitrogen is the same. What Dalton's Law of partial pressure says is that the total pressure would be equal to the pressure of the oxygen plus the partial pressure of the nitrogen. So that would be 4.48 atmospheres plus another 4.48 atmospheres, which would be 8.96 atmosphere. Pretty simple, right? Not a big deal. Well, it is a big deal, but it's not a difficult thing to consider. Now, the question is, how far can we go with this? So what I'm going to do is I'm going to talk a little bit about the types of problems we can look at. And to do that, I'm going to introduce something which is called the mole fraction, which is useful for talking about this. Mole fraction is the basis of this. What we will say is there's a symbol mole fraction, X, for an individual gas is equal to the moles of that gas divided by the total number of moles. We're going to call that the mole fraction. So for example, let's say that we have 1 mole of O2 and 3 moles of N2. There's a mixture, right? 2 different gases. The mole fraction for oxygen would be the moles of oxygen over the moles of oxygen plus the moles of nitrogen. That's the total number of moles. You're going to add them together. So that would be 1 mole over 1 plus 3, 4 moles. Now the moles cancel and you get 0.25. So the mole fraction of oxygen would be 0.25. Now, what if we wanted to know the mole fraction of N2? Well, that would just be the moles of N2 over the total number of moles. So that would be 3 moles over 4 moles, right? 0.75. Now notice those two add up together to be 1. right? The mole fractions of a mixture of gases should add up to 1, okay? Now, what I'm also going to do is I'm going to make the following claim. That since the pressure of a gas is directly proportional to the number of moles of the gas, right? P equals nRT over V. So as N goes up, P goes up, they're directly proportional to each other. The mole fraction of a gas is equal to the partial pressure of that gas over the total pressure. That's an interesting relationship, and it's a very useful one. Meaning that as the partial pressure of a gas in a mixture increases, the mole fraction should increase as well, or vice versa. Okay, so that's pretty nice. So what that does is it allows us to do certain types of calculations. So we can rearrange this to say that the partial pressure of an individual gas is equal to its mole fraction times the total pressure. So if you know the total pressure and you know the mole fraction of the gas, you can find the partial pressure of the gas. Okay, let me show you an example of that real quickly. So suppose that we have, again, 1 mole of O2 and 3 moles of N2, and the total pressure is, I don't know, 10 atmospheres. Let's find the partial pressure of N2. Right? What is the pressure of N2 in this mixture? Well, in order to do that, we need to know the mole fraction, because it's the mole fraction of N2 times the total pressure. Okay, well, let's find the mole fraction. We already did that, right? It's 0.75, right? It's 3 moles divided by the total number of moles, which is 4, so 0.75 times 10 atmosphere. Well, 7.5 atmospheres, right? So the partial pressure of nitrogen would be 7.5 atmospheres. So it's a pretty useful relationship. Okay. Now, I want to talk a little bit about the issue of vapor pressure, because that comes up in a lot of problems as well. And in particular, the vapor pressure of water is an issue. So sometimes there are experiments. So I'm going to talk about a figure in your textbook. This is figure 10.14. Sometimes there are experiments where we generate gases. We'll call it a gaseous product. And it's collected in water. Okay, so figure 10.14 shows that. So the idea here is suppose we have a test tube. And we're going to put a solid in there. The solid that I'm going to pick is potassium chlorate. And what happens with potassium chlorate is that it will react to form potassium chloride and oxygen gas. Okay? It requires heat. So I'm going to put a little delta symbol there, right? The delta above the triangle above the arrow means that you're heating it. So how do we heat it? We're going to use a Bunsen burner, right? There we go. So we're going to put a flame on it. A very nice hot flame, and it's going to decompose. It doesn't require any other reactants, just some heat. It's an endothermic reaction. And the potassium chlorate will form potassium chloride and oxygen. Let's balance it. Okay, so for every 2 moles of potassium chlorate that reacts, you'll get 3 moles of oxygen. Suppose we want to collect that oxygen. One way to do it is to put a tube in it. and to put that tube into the bottom of a collection tray that has water in it. We'll call it a trough, a water trough. So we have a little hole here. So as this decomposes, oxygen gas will bubble through the tube and then come up, and then we have water in here. Now what I'm going to do is I'm going to take an upside down graduated cylinder, like so. And initially I'm going to fill it with water. It's full of water all the way to the top, which is the bottom, because we've got it upside down, right? And what happens is, as the oxygen is less dense than water, it's a gas, it'll come up here and it'll bump up against here and it will begin to exert a pressure and it'll start pushing the water down. And so we'll start collecting the gas up at the top here, right? So that'll be gas there and it'll just push the water out. Now once it runs out, once all the water's out, then the extra bubbles will just start coming out like this. They'll just bubble out like that. So you can collect an entire container here full of oxygen gas. It's really cool. Okay. You can also collect oxygen gas from hydrogen peroxide. So you can actually buy hydrogen peroxide in the pharmacy, in the store, and you can heat it and generate oxygen gas as well. Okay. So suppose we do this and we're collecting this oxygen. We would say, okay, what is the pressure of the oxygen in here? What happens is, because this is open here, right? This is open here. The pressure due to the atmosphere is 1 atmosphere, 1 atm. What happens is, if the pressure in here is larger than 1 atmosphere, the excess oxygen will just bubble out. So it will stay at 1 atmosphere. It'll stay at the same pressure that we have in here. So what happens is, the pressure of the oxygen is equal to the pressure of the atmosphere. Because if it gets any larger, it'll just bubble out until it decreases to that pressure. However, there's a problem. And the problem is that water exerts a pressure as well. Now, I'm not talking about hydrostatic pressure. I'm not talking about the pressure of a liquid. So, for example, if you jump into a pool, you can feel the pressure of the water on your skin. What I'm talking about is what's called vapor pressure. And vapor pressure is very interesting. What vapor pressure is if you have a liquid in a container, so water is liquid in a container, it turns out some of that liquid on its own, just due to the energy of the molecules, will vaporize into a gas. So normally, if the container is open, air is flowing and it'll just like push that vapor away. Okay? But what can happen is, we have a closed container here. So in that closed container, let's say the water level is down to here. So this is your water level. And we have oxygen gas in here, right? This is the oxygen we're collecting. Well, here's what happens. The water will vaporize too, some of it, a very small amount usually. But some of the water will vaporize as well. So you'll actually have a mixture of gases in there. You'll have oxygen gas, but you'll have water as a gas as well. Now we call that, colloquially we call that humidity, right? We know that water can exist as a gas in the air, and we call that humid. The more humid it is, that means the more water there is in the gaseous state. It's not very much, but it's not insignificant in these calculations. So here's what happens. I made this claim that the pressure of the oxygen in this cylinder is equal to atmospheric pressure, but that's actually not true. What happens is, the total pressure inside the cylinder is equal to the atmospheric pressure. The pressure in here of the gases in here is equal to the atmospheric pressure. But we have two gases now, not just one. So that means that the pressure of oxygen plus the pressure of the water, the vapor pressure of the water, is equal to an atmosphere. One pressure, whatever the atmosphere is. Okay? So that's an issue. The vapor pressure of water. If we are collecting a gas in a container and the collection of that gas involves water, meaning that we're displacing the water from the cylinder in order to collect the gas, we have to take the vapor pressure of the water into account if we want to know what the pressure of the gas that we're collecting is. So what we would do is we would just take that equation and we would say that the pressure of the oxygen that we're collecting is equal to the atmospheric pressure, 1 atm, minus the vapor pressure of the water. Okay? Again, this is not hydrostatic pressure. This is not like the pressure of water on you. It's the vapor pressure of the water. Okay? Oops, I erased this. Let me rewrite this, sorry. Okay? So the pressure of oxygen for this reaction would be equal to, you just write it this way, the pressure of the atmosphere, because it might not be one atmosphere, it could be a little bit different, minus the vapor pressure of the water. Now, what is the vapor pressure? How much is the vapor pressure of water? And it turns out table 10.5 gives you some insight into that. Vapor, hey, let's spell it like the British do here. Vapor pressure. So there we go. Vapor pressure of the water. It depends on temperature. Remember, water boils. The boiling point of water is 100 degrees C. So as you approach 100 degrees C, the vapor pressure of water increases dramatically. So now let me give you a few values here. This is just some selected values from your table here. So I'm just going to pick a few. And the units we're going to use are in torr. So not in atmospheres, but in torr, just the way your textbook is set up. At 0 degrees C, water has a very low vapor pressure, but not 0. It's 4.6 torr. Remember, 1 atmosphere is equal to 760 torr. Okay, so that's pretty small. Let's see what that is as a fraction of an atmosphere. If you take 4.6 torr and divide that by 760 torr per atmosphere, it's pretty small, 0.0061. Okay, so that's a pretty small pressure. That's a small pressure at 0 degrees C. But as you increase the temperature of water, let's say you bring it all the way up to 20 degrees C. Well, that's close to room temperature. Now the vapor pressure jumps up to 17.5 torr. Still not a giant value. But remember, if we're collecting everything at 1 atmosphere, that's 760 torr. So that means the pressure of oxygen would be 760 torr minus 17.5 torr. So that's not that, that's significant, right? Like if you look at this second number and you compare it to the first, there's a real adjustment there. This is going to go down to about 742.5 torr. So that's significant. Now suppose you jump it all the way up to, let's say we're near metabolic temperature, 40 degrees C. Well, now the vapor pressure jumps all the way up to 55.3 torr. So if we were collecting this at water that was hot like this would be hot water. It's about close to 100 degrees Fahrenheit. The pressure of the oxygen would now be 760 torr minus 55.3 torr. Okay, now that is real significant, right? 55.3 divided by 760 that's about 0.07. So that's about 7% of an atmosphere. Okay, so that's not insignificant. Now suppose you go all the way up to 100 degrees C. Now this was not something we would do in terms of collecting oxygen or collecting a gas. Most likely we're not going to make the water 100 degrees C. But I want to point out that look what happens to the vapor pressure of water. 760, right? What that tells us is that once you reach the boiling point of the liquid, which is water, its vapor pressure is equal to an atmosphere. Okay? So the vapor pressure of a liquid increases with temperature until you reach the boiling point. 100 degrees C for water, right? We're just talking about water in this case. 100 degrees C. At the boiling point, the vapor pressure is equal to an atmosphere, 760 torr, right? So there you go. So that's significant. That is an important, it's not really that important for us right here in this discussion, but it's an important point in general understanding, which is that when a liquid is at its boiling point, at that temperature that it boils, the vapor pressure of that liquid will reach such a value that it's equal to the pressure of the atmosphere. Okay? So this is section 10.5.